Okay, so we are ready to start. Welcome everyone to the morning session. Today we're happy to have Bobby Acharya from ICTP, who will tell us about classifying special holonomy Kummer constructions. Let's welcome the speaker.
Thank you for this introduction, and thanks to Professor Yao and all of the many organizers and people involved in this wonderful Congress. It's really a pleasure to be here and see the new institution in operation and doing well, and also to meet many colleagues and friends that I haven't seen for some time. So this is a rough outline of the talk. So I'm going to give some very general introduction, where the focus will be on Ritchie flat manifolds, especially those with special holonomy groups. And then most of the results are on what's called generalized Kummer constructions. I will review Joyce's original construction of compact manifolds of G2 holonomy. So this was the first construction of such manifolds in the 90s. And then outline some of the results. So all of the work I'm talking about is done with Daniel Baldwin, who is a PhD student who just is Viva in London. And I'll kind of describe this classification that I'm talking about, or the classifications that I'll talk about, actually generate large amounts of data, like many manifolds, many orbifolds, many with all kinds of properties. So it's difficult to describe it all in detail. We're talking about tens of thousands of examples, but I will try and in fact, work is very, very new and fresh. So we're still processing data, but I'll just try and give you an idea of some of the things we've discovered along the way. So in particular, one of the main results is that this provides lots of new examples of compact G2 holonomy manifolds. And a nice kind of consequence, we weren't really planning to do that, but comes as a consequence of what we're doing. We have a classification of compact flat manifolds whose holonomy groups are contained in the exceptional Lie group G2. And they will have lots of applications as toy models for models of quantum gravity in Minkowski space. So let me begin with some introduction to the framework. So superstring theory and M theory is in my view, a kind of unifying framework for all of physics, which includes gravity. And remarkably, it's the only framework that we know of that predicts its own space-time dimension. Quantum field theory does not do that. And this dimension of space-time is 11. And this is also fixed by symmetries, in a sense. 11-dimensional space-time is the maximal dimension in which you can have a representation of the super Poincare group that contains particles of maximal spin 2. So at low energies, so we're talking about theories. If we take the low energy approximation, we should just think about space-time manifolds of dimension 11. When the 11 manifold is smooth, the theory is well described by a field theory, which is 11-dimensional supergravity. This is, I mean, it's in some sense a relatively simple theory. It has three fields: a metric, so space-time metric field, a three-form field, C, and a gravitino field, or sometimes called Rarita-Schwinger field, psi. So psi, a classical psi would be a section of the spin bundle with values in the tangent bundle. And if you set these matter fields to 0, so C and psi, and look at the equations of motion, the Euler-Lagrange equations of this field theory, they tell you that the Ricci tensor of G is 0. So manifolds for which the Ricci tensor vanishes are called Ricci flat manifolds, and the metric is called a Ricci flat metric. And just for these basic reasons, Ricci flat metrics play a key role in string theory. Now, since our universe is, by all appearances, four-dimensional, we are interested in solutions of this theory that don't have, for example, 11-dimensional Poincare invariants, but that have four-dimensional Poincare invariants. Because that's the space-time symmetry that we observe when we look around us. So if you impose that, then essentially it fixes this, I mean, up to some details, it fixes this 11-dimensional Lorentzian manifold to be a product manifold of a product of a 7-dimensional Riemannian manifold and Minkowski space-time approximately. And the metric, I mean, the simplest solution that has those properties would have some Riemannian metric g of x plus a Minkowski metric on the space-time part. And physically, we require this x7 to be small, suitably small, because we've got experimental limits on experimental constraints on the possibility of having extra dimensions of space. For example, you could have produced excitations of the extra dimensions at the Large Hadron Collider, and that sets a limit on, for example, the first eigenvalue of the Laplacian of this metric G. So we take x7 to be suitably small, and the equation, the Ricci flat equation, tells you that this 7-dimensional Riemannian manifold is also a Ricci flat manifold. So compact Ricci flat manifolds play a key role in string theory and M theory. So now let's just be a bit more general, because I want to give some overview on just say some general remarks on a few things which are known about compact Ritchie flat manifolds. So if the manifold is irreducible and compact, the Ritchie flat manifold has to have a finite fundamental group. If it doesn't have a finite fundamental group, it just means that you can add circle and tori factors up to some discrete isometries. And I'm not interested in those for the moment. And it's a fact that the only known examples of compact, simply connected Ritchie flat manifolds have special holonomy. And these are the only allowed special holonomy groups for Ritchie flat manifolds, for the simply connected ones. So in even dimensions, you can have SUK holonomy. Such manifolds are the famous Calabi-Yau manifolds. In 4K dimensions, you can have SPK holonomy, which are hyperkähler manifolds. And then in dimension 7 and 8, there are two exceptional cases corresponding to the holonomy groups, so-called exceptional holonomy groups, which are G2, the dimension 14 exceptional Lie group of rank 2, and spin 7. So it's not known whether or not there exist Ritchie flat manifolds of generic holonomy, and one can conjecture that compact stable Ritchie flat manifolds actually have special holonomy. So I wrote a sort of physics paper on that subject some few years ago. If you're interested in a more detailed survey about what's known and what kind of instabilities you can have. Yau and collaborators had a paper around the same time, which proves that all special holonomy compactifications of this type are stable. That's a sort of rigorous proof. Okay, I prepared one slide on what is known about compact Ritchie flat manifolds today. Let's discuss that offline. It's very technical, but it could be perturbatively stable, but then there's also non-perturbative instabilities that you can have. Okay, so if we just go through the holonomy groups, I'll tell you what's known in various dimensions. So for hyperkähler manifolds of real dimension 4n, in each given dimension, there's an existence proof of an example, at least one example. And in fact, the maximum number of examples known in a given dimension is 3. There are 2 examples which exist in all dimensions. And these manifolds, one series in dimension 4n is the Hilbert scheme of n points on a K3 surface. And the other one is related to the Hilbert scheme of n points on a 4 torus, a real 4 torus, but thought of as a flat hyperkähler flat space. And then in 12 real dimensions and 20 real dimensions, O'Grady, some decades ago, well, hyperkähler manifolds are simply connected. They can't be anything else. Well, for hyperkähler, it's actually 0. But in Calabi-Yau threefolds, you can have a non-trivial pi1. Anyway, pi1 is finite. Yes, yeah. Yes, I'm considering finite fundamental group. Yeah. And so, and so O'Grady provided two kind of exceptional examples in real dimension 12 and 20 some decades ago. And since then, which I think was around maybe 30 years ago, there has not been any new example of a compact hyperkähler manifold. And part of the motivation of this work was to try and classify these Kummer constructions, which may or may not lead to new examples. Okay, so in even dimensions, if we consider the Calabi-Yau case, so holonomy SUN in 2n dimensions, Professor Yau's proof of the Calabi conjecture provides many examples. But the compact Kähler manifold with vanishing first Chern class, the theorem shows the existence of a Calabi-Yau metric and families of Calabi-Yau metrics. So by far, what we know about compact Ricci flat manifolds is as a result of this theorem, because most of the examples by far are there. So there are many algebraic examples, and there are also generalized Kummer constructions. So examples you can make by resolving orbifold singularities in various ways, plus other constructions, which I don't have time to mention. And then finally, in the exceptional holonomy world, Dominic Joyce gave the first existence proof of these manifolds in the mid-90s. And I will review that generalized Kummer construction of Dominic's momentarily. And since then, there's been another construction, which I'm not going to review, which is called the twisted connect sum construction. That was first studied in detail by Kovalev and then developed significantly by Corti, Haskins, Nordstrom, and Pacini. And this led to millions of examples. If anyone's interested in the details of any of these, please come and talk to me during the meeting. So now, even though we have these examples, I think it's fair to say we still know very little about compact Ricci flat manifolds. For example, in a given dimension, we don't know if there are finitely many topological types or infinitely many topological types. So we don't know if there are finitely many hyperkähler or Calabi-Yau or G2 manifolds in the compact finite fundamental group category. And so we would definitely like to understand more about the geography. So the point about this geography is that, one point about it is that I feel we really know very little about what the possibilities are, even though we have lots of examples. Okay, so now I'll get slightly more technical and we'll talk about the Kummer construction of K3 surfaces from a couple of different points of view. So what is the idea here? The idea is to start with a four-dimensional torus. So that's a quotient of R4 by a four-dimensional lattice. Then, so that's step one. Then one restricts to 4 tori which have a complex structure. So this lattice should be compatible with the complex structure. And then in that case, I can write, for example, standard complex coordinates, Z1 and Z2. And in those complex coordinates, I can write a big bit. I can write dz1 wedge dz2. So that's a holomorphic symplectic form with real and imaginary parts, omega 1 and omega 2. And I can also write a Kähler form, which I'll call omega 3. So that's step 2. Step 3 is to find a finite group of automorphisms of this torus which preserves these forms, preserves this structure. So this structure of these 3 symplectic forms is called a hyperkähler structure. And in all dimensions, a hyperkähler structure is defined by 3 symplectic forms which satisfy some compatibility conditions. And one is interested in finite group of automorphisms preserving such a structure. And the simplest case of the original Kummer construction is when that group is just plus or minus the identity acting on C2. So it's clear that plus or minus the identity acting on C2 preserves the hyperkähler structure, and therefore the quotient by this discrete group is a hyperkähler 4 orbifold, because the forms descend to this quotient. Now, this is a singular space. It has singularities, and the singular set are just the order 2 points of this 4 torus, of which there are 16 singular points. These 16 singular points are modeled on the origin inside the kind of non-compact model, which is just C2 modulo plus or minus the identity. So this is a conical singularity, if you like, the simplest example. Now, this singularity, C2 mod Z2, has the Crepin resolution, which is given by the cotangent bundle of CP1, or equivalently, if you forget about the complex structure, the cotangent bundle of a 2-sphere. And it turns out that this smooth 4-manifold actually admits complete asymptotically locally Euclidean, which in this case just means locally asymptotically flat, hyperkähler metrics. So as a 4-manifold, it's as a 4-dimensional Riemannian manifold, it's a beautiful non-compact version of a Ricci flat space manifold. And in particular, one important fact about it is that it's geodesically complete. So these metrics were written down by Calabi, Eguchi, and Hansen. It's often called the Eguchi-Hansen manifold, and also discovered in a different coordinate system by Gibbons and Hawking. So, in other words, we get a hyperkähler structure on this smooth manifold. Now, you can essentially apply the same logic, but globally, and do a Crepin resolution of this singular orbifold, compact singular orbifold, and that produces a compact four-dimensional manifold. Now, what's happening here topologically is that you take this singular point, one way you can think of it, one way you can think of it is take the singular point in C2 mod Z2 and take a small neighborhood of that point, remove that neighborhood, so it's a ball. The boundary of that ball is the same as the boundary of the cotangent bundle of the sphere, which is a copy of RP3. And so you're sort of gluing in this cotangent bundle of the sphere and matching it to that boundary. But you see the cotangent bundle of the sphere is contractible to the sphere. It's a vector bundle over the sphere. So you're basically gluing in topologically non-trivial two-sphere. And when you do it at all of the 16 points, you're gluing in 16 different spheres in different, which give you a manifold with lots of topology. And in fact, the hyperkähler, this manifold turns out to be a holomorphic symplectic manifold which means it has a holomorphic 2-0 form, which in this case means that the canonical bundle of this complex manifold is a Calabi-Yau manifold. So Yau's theorem shows that you track the Kähler form under this resolution procedure, you end up with a metric of holonomy group SU2. So this and it turns out that this manifold is what's called a K3 surface. So I'm sure most of you already know. Now, so the fact is that because you produce complex surface which is Kähler and has 0 first Chern class, Yau's theorem implies the existence of a Ricci flat metric of holonomy SU2. But one can also think of this construction more from a more differential geometric perspective, because the metric that we start is flat on T4 mod Z2. Now imagine that the T4 mod Z2 is astronomical in size, and you have these 16 singular points which are at astronomical distances from each other. And all you're doing is cutting out a tiny neighborhood of all of these singular points. So that gives you a flat manifold with a boundary. And the boundary is going to be 16 copies of RP3. But these boundary regions are tiny. And then what you can do is glue in. You do this gluing construction to make smooth manifold that has now, instead of these boundaries, two spheres, topologically non-trivial two spheres in each of those regions. And you can simply approximate you can declare that you want to consider a metric which is approximately, looks like this Iguchi-Hansen metric near all of those regions, but is flat everywhere else. And then you can sort of smooth across. So that gives you some metric which is approximately Ricci flat. And okay, then you have to work hard, do some analysis to prove that you can perturb this to a genuine metric of holonomy SU2. So I refer you to papers of Topiwala and later an exposition of this by Simon Donaldson, which has much more detail. Okay, so that's the basic idea of the Kummer construction. There we did it with the simplest group, simplest discrete group, which was Z mod 2. One can actually classify all hyperkähler Kummer constructions in real dimension 4. And it turns out that there are 10 topologically distinct orbifolds that give rise to K3 surfaces. So Fujiki in the 80s, so part of doing this, you have to start with some T4 mod gamma. It has to have a complex structure. You have to look at the automorphisms of all possible such T4s and classify all the groups which preserve the A hyperkähler structure. So Fujiki did that, and I wasn't sure from his paper whether or not he actually got all the affine equivalence classes, but Daniel in his PhD thesis definitely did. And so there are 10 topologically distinct models for this. So there's 4 with cyclic groups, 3 with dihedral group of order 4, or no, it's order 8, sorry, D5 dihedral group of order, actually I can't remember what my notation is. T is the binary tetrahedral group. That gives rise to 2 distinct examples. Anyway, you get 10. 2 different affine equivalence classes because, so maybe I'm going to say this here. Yeah. So if you think about the Euclidean group, so on a torus you can have, or in Euclidean space, you can have rotational symmetry and also translations. So you can have many different subgroups of the Euclidean group which map to the same subgroup of the rotation group. And that's why I have the T here is actually the groups in the previous page are what we would call point groups, which in the case of flat manifolds, so in the case where gamma acts freely on the torus, so that the quotient is a manifold, these would be called the holonomy group of the flat manifold. Whereas the actual groups you want to classify are the space groups, and there can be many space groups for a given point group. And those are given by basically the affine equivalence classes. And there'll be, as we'll see, there'll be many more of those than holonomy groups. So that was, I'm just going to go up in dimension now as the talk goes on. So we did dimension 4. Then the next non-trivial dimension to consider, well, actually dimension 5 is also non-trivial, but I'm not going to talk about it. Dimension 6, we want to consider Kummer constructions of Calabi-Yau threefolds, so quotients of some 6 torus by discrete group preserving a Calabi-Yau structure. So here I've written the model Calabi-Yau structure. Small omega is a standard model for a Kähler form on C3, and big omega is a standard model for a holomorphic 3 form on C3. which so resolving yeah, these produce different K3 surfaces, but the underlying topological 4 manifold is the topological K3 manifold, but these produce different K3 surfaces. Okay, so this case was actually completed in in 2012 by Fisher, Ratz, and Tirado. And I'm not going to survey their results in much detail, but when you go up from Calabi-Yau 2 folds to Calabi-Yau 3 folds, you go from 10 to 469. This is the answer that they gave. And all of these, when gamma acts non-freely, can be desingularized to give any, in fact, a huge number of Calabi-Yau 3 folds, if you think about it carefully. Because a given orbifold will have many topologically distinct desingularizations if you're in the Calabi-Yau 3-fold world, because you can do partial resolutions, then deform, and all kinds of becomes very complicated. Okay, so this is not the number. Well, this is the number of orbifolds that you get, but if you think of it in terms of some huge moduli space emanating from that, these 469 distinct points in moduli space are many branches which are topologically distinct. Okay, so that's the Calabi-Yau 3-fold case. Again, we can, if anyone's interested in detail, there's lots of stuff. I encourage you to look at this paper. It has lots of details, and I'm happy to discuss it with anyone. Next, I will move to the 7-dimensional case of G2 holonomy. Sort of the main results I wanted to share with you. So first of all, I'll tell you some very basic things about compact 7 manifolds with holonomy group G2. So if the holonomy group is of this Riemannian metric G is isomorphic to G2, then the fundamental group of X must be finite. And in that case, the following statements are equivalent, that there exists a 3-form phi which is parallel with respect to the Levi-Civita connection of the metric G. So this 3-form phi is the analog of these hyperkähler forms or Calabi-Yau forms in the other cases. Now, the condition that the 3-form is parallel is also equivalent to phi being closed and co-closed with respect to the metric for which phi is parallel. And finally, which is something we will use in our classification, is that there exists unique, up to scale, parallel spinor field on X. So S of X is the spinor bundle, and eta here on this slide at least is the spinor which is parallel with respect to the Levi-Civita connection. So essentially it's a constant spinor, globally defined everywhere. I'll describe in different ways a model in the flat case, since we require this for studying quotients of a flat R7, and it's good to see this anyway. So phi 0 in some model, I've written a model for phi 0. One way you can think of this is that you think of R7 as the imaginary octonions. One basis for phi would be the structure constants of the imaginary octonion, because G2 is the symmetry group of the imaginary octonions. So there are different models that are actually very relevant to how compact G2 manifolds are constructed. One, if you think about this in one way, you can write, if you split R7 into R4 plus R3 with coordinates, 1, 2, 3, 4, and 5, 6, 7, then you can relate phi 0 to a hyperkähler structure on R4 in the way I've described there. So phi would just be the dot product of the hyperkähler structures with the coordinate one forms on R3 plus the volume form on R3. Another way of thinking about it, to relate it to the Calabi-Yau threefolds, is if you write R7 as C3 plus R, and here my R, if I wanted to match, if I've done it correctly to match my previous definition, my R is in the fifth direction. Phi 0 would be the Kähler form wedge dx5 plus the real part of the holomorphic 3 form. And so these things have to be true in flat space because SU2 is a subgroup of SU3, which is a subgroup of G2. Okay. So now let's, in the same way that we reviewed the Kummer construction, we're going to review Joyce's construction of the first examples of compact G2 manifolds from the 90s. So the basic idea is, as we've been discussing, we consider some T7 with some finite group of automorphisms preserving a G2 structure phi 0. Can be exactly the phi 0 I wrote on the previous slide. And the basic idea of Dominic's was to choose this group of isometries such that the singular set has components which are either of codimension 4 or codimension 6. Sorry, there's a typo here. Meaning no codimension 7 singularities. So in this situation, near any, again, just think of an enormous cosmological sized 7 torus modulo this discrete group action, and go near any component of the singular set, these will either, if they're codimension 4, they'll be locally modeled on the origin times T3, or perhaps a finite quotient of that in C2 mod H times T3. These are exactly of the kind we've just been discussing in the hyperkähler case. Or they'll be of the form C3 mod some finite group times S1, and this H prime and H will be a finite subgroup of SU2. H prime will always be a finite subgroup of SU3, meaning that these local models are actually Calabi-Yau. And for example, it's known that for every finite subgroup of SU3, there exists at least one desingularization that admits a complete, important word, complete Ricci flat, asymptotically flat metric. Because G2 is exactly because G2 preserves a spinor. These have to be groups which preserve the spinor everywhere. And so in particular, locally, they have to preserve a spinor. And so the one you described, C times T5 modulo a group at C modulo ZK, does not preserve any spinor. So yes, an excellent question with an important reason for this. You can. For Joyce's construction, we're excluding codimension 7 singularities because we don't have any version of analog of Calabi-Yau theorem. Yeah, we don't have a simple, obvious way to study such singularities. Of course, we have studied such singularities, and they're very important. And I'll come back to them later. So we want to. Dominic only wants to consider. You choose gamma in such a way that you don't have such singularities. The generic gamma will have such singularities, as we will see. So you basically you follow exactly what we've said. You glue in model complete metrics into these regions. That gives you an approximately Ritchie-flat metric. So you have the Ritchie-flat metrics in these tiny regions coming from the model metrics. And then you have the flat metric in the bulk of the space. And you make some ansatz for that. In such a way that the size of the covariant derivative of the corresponding free-form is small. Now, Dominic did a lot of hard work. When I say he did some serious perturbation theory, he did some serious analysis and perturbation theory to prove a theorem that morally says that in this kind of situation, you can always perturb your metric, your model metric G prime by some small perturbation delta G, which gives you a Ritchie-flat metric of G2 holonomy. Oh, yeah, so you choose it such that the topological manifold you make has finite fundamental group. So, no, this gamma is some complicated group. It acts in all directions of the space. So the fundamental group of the manifold that you get is actually the group, is the quotient of the full group by the group generated by elements that have fixed points. But usually that's the whole group. So if you look at R4 modulo, if you look at T4 mod Z2, but viewed as a quotient of R4 by an infinite group, which is essentially semi-direct product of a lattice and Z2, the group generated by the elements that have fixed points on R4 is actually the whole group. And that's why the manifold that you get in the end is simply connected. And so all the manifolds I'm talking about here will have finite fundamental group, apart from the flat manifolds. Okay, so at the moment, the state of the art is that any construction of compact G2 holonomy manifolds has to use Dominic's theorem or a variant of it. So you have to be able to construct a three-form whose covariant derivative is sufficiently small to apply the theorem. And under these assumptions, that is true. And that's what Dominic went to great lengths to prove in the 90s. So we, meaning Daniel and I, just take this, apply it to do our classification. But before I do that, let's just look quickly at Dominic's simplest example to see how it works. So his first example that he described, the group gamma is just order 8 abelian group isomorphic to Z2 cubed, has 3 generators, alpha, beta, and gamma. The torus that it's going to be acting on is just the square torus. So we take it as a product of 7 circles, all of unit periodicity. And there's the 3 form from before. And this is how alpha, beta, and gamma act. So you see that alpha acts in the way analogous to the Kummer construction of the K3 surface. Beta, so all alpha, beta, and gamma, their projections to the rotation group are all diagonal matrices of order 2 with 4 negative eigenvalues. But you see beta includes some non-trivial translation in some of its elements. So this means you take x2, you map it to minus x2, plus half, plus a half, there's half a period on that circle, and so on. So in this example, alpha, beta, and gamma are the only elements which act non-freely. All the other elements, all the alpha times beta, etc., beta times alpha act freely. So the singular set will have 3, will be generated by the fixed points of alpha, beta, and gamma separately. And it turns out that the singular set is 12 copies of T3, 12 T3, so it's a codimension 4 fixed point set, which is the union of 12 copies of T3. 4 of them are from alpha, 4 of them are from beta, and 4 of them are from gamma. And near each one, they're modeled on exactly our nice model, C2 mod Z2. So that means that Joyce's conditions are met, and the approximate G2 structure that you get by gluing in a Gucci-Hansen matrix times a flat metric on T3 can be perturbed to a genuine G2 holonomy metric. The manifold you get is simply connected and has B2 equals 12 and B3 equals 43. One thing I didn't say is that harmonic 3 forms control the moduli space. The third cohomology group is a model space to the moduli space of G2 holonomy metrics. So this actually produces a 43-dimensional family of G2 holonomy metrics, which is enormous. We still don't really know much about the global properties of that moduli space. Okay, so Dominic went on and he considered of order something like 20 to 30 models, so 20 to 30 different choices of T7 and gamma, so 20 to 30 orbifolds. Most of them had just codimension 4 singularities, but there was also some examples with, handful of examples with codimension 6. And then resolving these in different ways leads to a few hundred compact G2 manifolds, all of which are listed in and described in his book from like 2000. So what have we done with Daniel? The goal is to classify all such orbifolds, and we're essentially there. We're just working out some of the details. So these results are sort of it's like a preliminary announcement of some of the things that we've found. So we find thousands of new orbifolds, at least 6,000. And many of them, although we haven't actually counted how many, but it's clear that there are many, satisfy the conditions from Dominic's, to be able to apply Dominic's powerful theorem. So you get many new G2 manifolds. We find many new, actually, compact flat manifolds that have parallel G2 structures. So those are interesting, and that was a bit of a surprise. So how do we actually do this? Well, you have to look at all 7 tori. So every 7 torus, you find the automorphism group. So just to fix in your mind, for example, say the 7 torus was the maximal torus of E7, then the automorphism group is the Wahl group of E7, or contains, plus the outer automorphism. And so if you're able to describe coordinates and generators for this group, you can then attempt to list all of its discrete subgroups. So this is some enormous group. You can then list all of its subgroups. So we do that using the GAP software package, because you can't really do this stuff by hand. Then we lift each of these subgroups to spin 7. So they're spinor lifts, of which there'll be more than one spinor lift for a given group. And then we ask, does any of those lifts preserve exactly one spinor? And if it does, it means the original group preserves a G2 structure, phi 0. And then, these groups H alpha are what I was referring to as the point groups, but then one has to classify for each point group all of the affine equivalence classes that have that group as the point group. And again, we do that using GAP, and plus we have to write some code. So Daniel's written a very nice code to do this important last step. Then once you have all the examples, you have to then analyze the fixed point sets. That's also, you have some complicated group acting on some 7 torus. You have to compute the singular sets of that quotient. Again, one can do that remarkably using a computer. These are things which I dreamt about as a PhD student. Never imagined that would actually be doable. So just to give you an idea of something slightly more concrete than just these things, let's look at the indecomposable 7-dimensional lattices. So what does that mean? That means any lattice for which the automorphism group is a maximal, irreducible, finite subgroup of GL7Z. There are 7 of those. They're described sort of geometrically by Conway and Sloan in this paper. I don't know if you can read that, but it's E7, this is a variant of E7, this is A7, a variant of A7, this is D7 and various variants of D7, and then on the right-hand side you can see the order of the automorphism groups. But the nice thing about this paper is you can write down coordinates and actually carry out this exercise. So if you take this indecomposable cases, then we find more than 6,000 topologically distinct G2 orbifolds, which arise from just 453 point groups. So that's one of the main results, and this is the sort of database that we're mining through now. There were some nice surprises. This shows that there exist examples of compact G2 holonomy manifolds with 3-dimensional moduli space. So these are the first examples with such a low dimensional moduli space. From these irreducible, indecomposable cases, there are 171 compact flat manifolds. So these should give rise to what might be called the simplest four-dimensional quantum gravity, supersymmetric quantum gravity theories in 4D. They have two moduli at least. I misspoke yesterday. So but we haven't finished the classification because we have to look at the reducible 7 tori as well. So one question is, can you have a compact flat G2 manifold with B3 equals 1? Now, many of them have codimension 7 singularities, and these should give rise to very interesting four-dimensional physics. This is a subject which should be studied in much more detail, and there are thousands of these examples. This is just to show something concrete. This is the group action as a subgroup of GL7Z for this example that has low dimensional moduli space, B3 equals 3. So you can see these are the generators of the point group, which is some group of order 21. And this is how they act on the torus in these nice coordinates. This is a formula for the 3 form, just to be even more concrete, although that's harder to write down in general. I'm running out of time, but this is just to give you an idea of some of the data that we generate in terms of the fixed point set. So space group number 1 out of 9 means there's a point group which is an order 8 group. I think this is dihedral group of order 8, if I'm not mistaken. And this example gives rise to 9 distinct models with the same holonomy group. And then you can see there's examples with codimension 7. This is an example which you can resolve using Dominic's theorem because there's only codimension 4, etc., etc. So we're sort of going through this information. We'll make all of this eventually publicly available and provide the relevant data for each example. And we welcome if anyone has suggestions or experience on how one should do this and what kind of information we should include, please come and talk to me because I have no prior experience about such things. Okay, we did something for the hyperkähler case as well. You can have a look at our paper, but I'm really actually 2 minutes over time. So I'll just close by saying, we can actually go much further than this. Presumably, we can do all T8 mod gamma special holonomy, which means Calabi-Yau, hyperkähler, and spin 7, and we could probably do higher dimensional hyperkähler as well, but we're not sure at what point one gets limited by computational limitations. So there's also some interesting computational aspects of this at some point. So thank you for your attention.
We have time for maybe 1 or 2 brief questions.
Some examples, yes, but very specific ones. If the theory of at the codimension 7 singularity has appropriate couplings corresponding that correspond to the resolution moduli, then yes. So if it was a CFT, it would have, marginal coupling. No, that's basically completely understood. In the case, so those arise from codimension 4 strata of the singular set. And for manifolds with only codimension 4 singularities, Daniel and I, this is also another thing that I didn't think was possible when I was doing my PhD, when I first started studying these things. But we have a complete classification of the physics of those if you have only codimension 4 singularities in a G2 manifold. And it's quite simple.
Okay, let's thank the speaker again. And we'll be back in 10 minutes.